The third video in our acid-base equilibrium unit. In this video we're going to focus on the equilibrium constant associated with acids and bases and how to actually calculate that constant as well as pH from various values. So before we actually dive into the video that's based on sections 6 to 8 in chapter 16, first we're just going to focus on some review. So keep in mind, strong acids completely ionize in water. Ionize means that it essentially breaks up into its ions. It does react with water to form ions. Strong acids, 100% ionize, so you use a single arrow. So HCl, which is aqueous, plus H2O yields H3O plus Cl minus. Remember, H3O plus is the same as H plus. We use them interchangeably. So essentially, there are no acid molecules remaining in solution after this reaction has occurred. So the equation usually does not contain equilibrium arrows. If it's a strong acid, it's a single arrow. That means KEQ is much, much greater than 1. There are only products at equilibrium. Only H plus and Cl minus, no HCl. So their conjugate bases have negligible tendencies to become protonated. That means that their conjugate bases are not actually basic at all. They are neutral anions. Neutral in terms of basicity. So the conjugate base of a strong acid is a neutral anion. In terms of strong bases, they completely dissociate in water. That means that they completely break apart into their ions in water. So we have sodium hydroxide. Notice it's a single arrow because it dissociates 100% in water to form Na plus and OH minus. So much like strong acids, there are no base molecules, no NaOH molecules remaining in solution. There are only Na plus and OH minus, so KEQ is much, much greater than 1. We have only products after the reaction has occurred. So the ions, the cations, do not want to attract an OH minus at all. They have negligible tendencies. So that means that the cation of a strong base is a neutral cation. Any other acid is a weak acid. So any besides the 7 is a weak acid. They only partially dissociate. So what that means is you're going to have some of this acetic acid, but not all of it's going to break apart into the ions. You're only going to have a little bit that's going to dissociate into the ions to give us H3O plus and the acetate ion. That's why we have this double arrow. So they exist in solution. So if we have a beaker of acetic acid, you're not only going to have H3O plus and C2H3O2 minus, you're also going to have molecules of acid. Typically, weak acids are going to be composed predominantly of the acid molecules. Their conjugate bases are weak bases. So the conjugate base of acetic acid is the acetate ion. Because this is a weak acid, this is a weak conjugate base. So besides the non-neutral anions, weak bases tend to be nitrogen-containing compounds. So what this means is, besides anions that are conjugate bases, typically other weak bases have nitrogen in it, such as ammonia. Ammonia is NH3. So not all compounds that contain hydrogen are acidic. Remember that we have some extremely, extremely weak acids that we don't consider them acids at all. Typically, we see OH minus, H2, and CH4. These have negligible acidity. That means that they're not acidic at all. They're neutral. Their conjugates are actually very strong bases. Oxide ion is a very strong base. When we look at ions, most anions are weak bases. So most anions are weak bases, most cations are weak acids. Although any anions from a strong acid and any cations from a strong base are neutral. The reason that we can remember that anions are bases is because the anions come from an acid. You always have to have an acid-base pair. The cations come from a base. You always have to have that acid-base pair. So let's compare strong and weak acids. Strong acids completely dissociate. Weak acids only partially dissociate. So take a look at this particle diagram. Here's a strong acid. Notice you have no acid molecules remaining. It's only ions. It's only H3O plus and A minus. In the right container, we have the weak acid. Notice we have acid molecules and then we have ions. Mostly we have acid molecules. This is a weak acid. It only partially dissociates. So where does this acid-base strength ranking come from? How do we know if something is a strong acid or a strong base or weak acid or weak base? Well, we have to actually look at KEQ. We look at the equilibrium constant. Since weak acids and bases are in equilibrium, we can actually write equilibrium constant expressions. So in looking at the reaction of a weak acid with water, remember HF is a weak acid. So we have weak acid plus water. We can actually write the equilibrium constant Ka. Ka is the acid dissociation constant. Remember we had KEQ, we had Kc and Kp. Well, now we have Ka. All this is saying is this is the equilibrium constant of an acid dissociating or an acid ionizing. So we can write Ka. We do products over reactants. Why don't we include water? It's a liquid. Then we can also do the same thing for a base. We can look at the equilibrium constant Kb. So we have a weak base reacting with water, and we get Kb, the base dissociation constant, the same way we do products over reactants. So for a weak acid, we have the acid dissociation constant. The reason that we can only do this for weak acids is because we have this double arrow. We can't do it for strong acids because we're not at equilibrium. There are no reactants at equilibrium. We only have products, so it's not even an equilibrium reaction. So when we have Ka, this table shows us different values of Ka. The greater the value of Ka, the stronger the acid. And that's because that the magnitude of Ka actually indicates the tendency of an acid to ionize in water. Because the larger the value of K, the more products you have. That means that it ionizes more. It breaks up more into its ions. That's a stronger acid. If Ka is smaller, that means we have more acid at equilibrium, which means it's not breaking up at all. So the greater the value of Ka, the stronger the acid. When it comes to Ka and Kb, the value of Ka or Kb indicates the extent to which the acid or base ionizes. So the larger the Ka or Kb means more products. That means it's going to be a stronger acid or base. Weak acids have larger Kas. Weak bases have larger Kbs. So if Ka is large, it's going to be a stronger weak acid. If Kb is large, it's going to be a stronger weak base. Now you want to bookmark Appendix D because you're going to be using this a lot. This is where your values for Ka and Kb are. Remember, these are constants assuming you're at the same temperature. Assuming you're at 25 degrees Celsius, you can use these Ka and Kb values in Appendix D typically to find the pH. So Ka and Kb are simply equilibrium constants for acid ionization or base dissociation. So what we're going to start looking at is the method for calculating Ka from pH. So what we actually can use Ka for is to find the pH when a solution is at equilibrium. We can also go backwards and use the pH to find Ka. A lot of times the reason that that is useful is because if we calculate Ka, we can compare it to the list of Ka values to actually figure out what acid it is. So if you actually have an unknown acid, you don't know what it is, you can calculate the Ka and you can determine the acid. So in order to calculate Ka from the pH, you need to know all the equilibrium concentrations. So what we have to do is we have to use an ICE table. We're going to actually be using a lot of the skills from the equilibrium unit in this section as well. So we're going to be using an ICE table. Then what's really, really important is that the pH gives the equilibrium concentration of H+. So when they give us pH, we know the concentration of H+ at equilibrium. Then we can actually substitute these concentrations in and we can solve for Ka. So let's look through an example. It says the pH of a 0.1 molar solution of formic acid at 25 degrees Celsius is 2.38. So pH is 2.38. We have our initial concentration of 0.1 and it says to calculate Ka. Well, what we need to do first is write the equation for the equilibrium reaction. So we have formic acid at equilibrium, double arrow, with H+ and HCOO-. Now most weak acids are going to consist of carbon, hydrogen, and oxygen. And that's exactly what this shows us. This weak acid is carbon, hydrogen, and oxygen. So the first thing that we have to do is write the equilibrium reaction, simply the ionization of the weak acid. Then we write the equilibrium constant expression. Notice we don't even include water because it's a liquid. So we have H3O+, same as H+. Okay, you can put H+ here. That's fine. times the formate ion divided by the concentration of formic acid. So now we know the Ka expression. Then, to calculate Ka, we need the equilibrium concentrations of all three of these. So we're going to make a nice table. We know our initial concentration. Initially, we don't have any ions, right? It hasn't ionized yet. Then what we need to do is we somehow need to find the equilibrium concentration based on what they've given us. Well, they give us pH, and the pH, again, gives us the equilibrium concentration of H+. So we can find the concentration of H+. Because it's a 1-to-1 ratio of H+ to formate, those two concentrations at equilibrium are going to be the same. So if we find the concentration of H+, we take 10 to the negative pH, we get 4.2 times 10 to the negative third. That's the concentration of H+, which equals the concentration of the formate ion. Now what we can do is set up our ice table. We know our initials. We know our changes because we know equilibrium. Okay, these concentrations that are in red, these are the ones that we know. We calculated equilibrium concentration of H+, that's equal to formate because it's 1-to-1. So to get from 0 to 4.2 times 10 to the negative third, you have to add that. But because it's all 1-to-1, instead of adding like we did in the products, we have to subtract 4.2 times 10 to the negative third from formic acid. So at equilibrium, we have 0.1 minus 4.2 times 10 to the negative third. But the amount of formic acid that ionizes is so small, right? It's 0.0042. It's so small compared to the initial concentration that we can actually just ignore it, and we're just going to keep it at 0.1. So now we have all the equilibrium concentrations. This allows us to calculate Ka by plugging back in to this Ka expression. So we have our equilibrium concentrations, and we find Ka is equal to 10 times 10 to the 1.8 times 10 to the negative fourth. Now we can check our answer, and this is reasonable. This 10 to the negative fourth is reasonable because the Ka for a weak acid is usually between 10 to the negative second and 10 to the negative 10th. So this is a pretty reasonable answer. So Ka equals 1.8 times 10 to the negative fourth. This is very similar to when we calculated Kc. Right? We used concentrations. The only difference is this is now for an acid ionizing at equilibrium. Remember that Ks do not have units, so it's just a value. Now, if you need this exact exercise more step by step, take a look at sample exercise 16.10 in your book, and that can guide you through more step by step than what we just did. So now we're going to go backwards, and we're going to use Ka, which is given in Appendix D, to calculate the pH for weak acids. So first you're going to start by writing the balanced chemical equation that clearly shows equilibrium. Then you're going to write the equilibrium expression. So you're going to write Ka equals, and you're going to do products over reactants. And you want to look up the value for Ka in Appendix D. Then you're going to write down all of your concentrations that you know. You're going to make an ice table, except for water because it's a liquid. Then we're going to be doing ice tables just like we did before. If you don't know the change, we're going to use X. Then we're going to plug everything in to the equilibrium constant expression. We're going to plug everything in to the Ka expression. So here's another example that we're going to look at. It says calculate the pH of a 0.30 molar solution of acetic acid. Right? Acetic acid is a weak acid. So we have our equilibrium reaction here. Acetic acid, after it I want you to put AQ in parentheses because acetic acid is aqueous. For water I want you to put a liquid, L in parentheses, and then H3O plus and the acetate ion are both aqueous. So I want you to put the states of matter in parentheses. So here's our equilibrium reaction. Then we can write our Ka. We know that Ka equals H plus, remember you can use H plus if you prefer, H plus times the acetate ion divided by acetic acid. That's your Ka expression. So you have products on the top, reactants on the bottom, that equals Ka. And then you can look Ka up in Appendix D. So your Ka, if you look it up in Appendix D, is 1.8 times 10 to the negative fifth. Then we make an ice table. We have initial, change, and equilibrium. Our initial of acetic acid is 0.30. We don't have any ions to start. Now it doesn't give us anything else at equilibrium. We don't have pH. So what we have to do is use X's because we're trying to find pH. So then what we can do is use x. So minus x, and plus x, just like we did with ice tables. Then we do 0.3 minus x, and x. So here's our example continued on. We have our Ka expression again, and now what I did is I simply plugged in x's for the products and 0.3 minus x for acetic acid. Now we can assume that x is much smaller than 0.3, and if we make this assumption, 0.3 minus x just becomes 0.3. That means that x is so small that we're just going to ignore it, only on the bottom. So the problem becomes a lot easier because we don't have to use the quadratic formula. So if we plug everything in, we have x squared divided by 0.3. Okay, again, because we made this assumption. Now if you make this assumption, make a note of it. So whether it's a book problem or a free response question, put a little asterisk that says assumed x is much less than 0.3. And to make this assumption, Ka needs to be a pretty small value. Notice that Ka is 1.8 times 10 to the negative fifth. That means that you have 4 zeros in front of this. So that's a pretty small number. So we can make this assumption and feel pretty good about it. So we've made this assumption. When we solve for x, we find that x is 2.3 times 10 to the negative third. Now think about what x is. Look back at your ice table. X is equal to the H plus concentration. Now we're not trying to find H plus concentration, we're trying to find pH. So take the negative log of what you find, and you find that the pH is 2.64. So notice that we have to use ice tables because not all of the acid is ionizing to give H plus. We have to use an ice table because only some of it ionizes. Now when we make assumptions that x are very small, what we have to do is we have to check the validity of it by calculating percent ionization. So percent ionization is simply another method to assess acid strength. So for this general reaction, percent ionization can be calculated as the H plus concentration at equilibrium divided by the initial acid concentration. And then because it's a percent, you multiply it by 100. So the higher the percent ionization, the stronger the acid. That's because strong acids ionize 100%. So if you have a weak acid and it has a 50% ionization, that means that it 50% of the time will ionize into H plus and whatever the anion is. So calculating percent ionization. We're going to be using the last example that we just looked at. So percent ionization is the H plus concentration at equilibrium divided by the initial acid concentration. So if we plug both of those values in that we got from our ice table, we can actually calculate percent ionization. And when we solve for percent ionization, we actually find that it's 0.77%. So this means that acetic acid only ionizes 0.77%. So as a general rule, if x is less than 5%, in this case it is. So if x is less than 5%, we can assume x doesn't matter. So it's okay that we ignored x on the bottom. But if your percent ionization is greater than 5%, you're going to have to use the quadratic formula to solve for x. So comparing strong and weak acids again. So remember that strong acids, the initial concentration of the acid is equal to the H plus concentration, assuming that it's monoprotic. For weak acids, though, your initial acid concentration is going to be greater than your H plus because your acid does not ionize all the way. So this actually is going to create a difference in conductivity and rates of chemical reactions. So reactions are actually going to happen much faster in strong acids, and strong acids are actually better conductors than weak acids. Again, because you have more ions moving around in the solution. So we've been talking about monoprotic acids a lot. Well, you can also have polyprotic acids, and polyprotic acids, polyprotic, more than one proton. So polyprotic acids have more than one H. And when you're looking at polyprotic acids, it's always easier to remove the first H than any other H after that. And table 16.3 down here actually shows the Ka values for each of the H's that you'd have to remove. So if the successive Ka values differ by a factor of 10 to the third, we can usually get a good approximation of the pH just by looking at the first Ka value. So if you actually take a look at, for example, carbonic acid, notice that it's 10 to the negative 7 and 10 to the negative 11. That differs by 4 factors of 10. So we can actually get a pretty good idea of the pH just by focusing on the first Ka. So now we're going to look at weak bases. We looked at weak acids, now we're going to look at weak bases. Now, weak bases, everything is the same as weak acids, except now instead of focusing on Ka, we're going to focus on Kb. So ammonia, NH3 is a weak base. So weak bases remove protons from substances, right? So down here, NH3 is going to take the proton from water. Like weak acids, weak bases have an equilibrium constant, but it's called the base dissociation constant, or Kb. The equilibrium calculations are going to work the exact same way as weak acids, except, like I said, instead we're going to be using Kb. Table 16.4 shows us a list of weak bases along with their Kb values. So just like with weak acids, the higher the Kb, so the larger the Kb, the stronger the weak base. So you can actually put all of these weak bases in order from strongest to weakest based on the Kb value. So I'm just going to go through very quickly another example looking at Kb now instead of Ka. So this says, what is the pH of a 0.15 molar NH3 solution? So just like we did before, now we're finding pH, and now NH3 is a base. So in your notes, I want you above NH3 to write base, because that's going to kind of determine what we have to use. So first thing you're going to do is write the equilibrium reaction. So NH3 is aqueous, H2O is a liquid, NH4 plus and OH minus are both aqueous. So write in those states of matter. Then we're going to write the Kb expression. We have products over reactants. We don't include water because it's a liquid. So you're going to write your Kb expression, and I want you to look up the Kb in Appendix D. Get used to using Appendix D, so you're going to want to bring your book to class. Remember, Ka, Kb values found in Appendix D of your book, so bookmark it. Then we're going to make an ice table. So we found Kb to be 1.8 times 10 to the negative 5th, so we can plug that in to our equilibrium expression, and we're going to use an ice table. The initial concentration is 0.15 molar. We have 0 for our ions. We have minus x plus x plus x. Okay, so we have 0.15 minus x, we have x, and we have x. We plug these values at equilibrium in to Kb. Now, if we assume that x is much less than 0.15, make a note of it, right? X is much less than 0.15, we can actually ignore this minus x on the bottom. Reduces our need to do the quadratic formula. So then 1.8 times 10 to the negative 5th equals x squared divided by 0.15. And we can solve for x, and you get x equal to 1.6 times 10 to the negative 3rd. Now remember what x equals. Okay? X is a molarity, and x is the molarity of OH minus. Okay? Label what this is. Right? So this is equal to OH minus concentration. Now if you take the negative log of this, what are you actually finding? You're finding the POH, and POH is equal to 2.80. Now, the problem asked for pH, so then you have to do another calculation to find pH. So make sure that you label everything that you're doing. Notice it goes through the same method, though, as using equilibrium and using ice tables. So there are two types of weak bases. The first type is a neutral substance that has lone pairs of electrons. The lone pairs of electrons can accept the proton. It's like ammonia or amines. Amines have nitrogen groups, or you can have anions of weak acids, okay? As long as you have somewhere for the H to go. Finally, we're going to look at the relationship between Ka and Kb. So for any conjugate acid-base pair, you have a Ka and a Kb value. They are related because if you multiply Ka by Kb, it equals Kw. If you actually want to see the derivation of this equation, which is pretty cool, look at section 16.8 in your book. It actually shows how you cancel everything out to get this equation. So for any conjugate acid-base pair, the product of the acid dissociation constant, which is Ka, times The base dissociation constant, which is Kb, is equal to the ion product constant of water, which is Kw. So therefore, if you know one of them, if you know Ka, you can find Kb. If you know Kb, you can find Ka. So even if Appendix D only gives you Ka, you could actually find Kb using this equation. Now, one thing to make note of is as the strength of the acid increases, which means Ka is increasing, the strength of its conjugate base has to decrease because Kb must go down because Kw is a constant. So as acids get stronger, their conjugates get weaker. This is actually why the conjugate of a strong acid is neutral, because its Ka is already, so high. So you want to know the relationship between Ka and Kb, as well as how to calculate pH or Ka or Kb using weak acids and weak bases. We're going to be doing a lot of practice in class, but if you do have questions, please make note of them and bring your questions to class.